All right, good morning. This is calculus, and this is 10.3, parametric equations. But now we're going to start taking some derivatives and showing you how to find slopes and arc length. So if a smooth curve, C is given by the equations x equals a function of t and y equals a function of t, all right, g of t, if you will. The slope or the derivative at point xy is the derivative of the y's up top, derivative of the x's on the bottom. So if you have a parametric equation where it's x equals something with t, y equals something with t, take the derivative of the y's up top, take the derivative of the x's on the bottom. That's it. All right, I think we can show one. Before I do, I want to show you higher order derivatives because this is where things get silly. All right? Higher order derivatives, like a second derivative, and they'll ask you this on the AP exam, is the derivative of the derivative, but it's not what you think. It will equal, you ready? d dt of the derivative, which is dy dx, okay? And then on the bottom, however, okay, on the bottom, it's just going to be dx dt. So this was the original derivative of the x, the first derivative. That's all that is. This is the first derivative, if I did anything good there, with respect to x. So the same thing you did in the first time. And you might say, well, why is that? I don't know if you care, but if you kind of care, okay, then we'll get, you don't care. I don't think you care, but that's the big deal, all right? So I made up a problem here. Okay, here's a problem. Nice little problem. It says find the slope and the concavity. So that takes care of both derivatives. That's why the second derivative is so important, because you know it measures concavity or tells something about the concavity. So what we're going to do is we're going to use that formula. And we're going to say, all right, let's do it in blue maybe, not red. And let's work on the slope. dy dx is equal to the dy dt. So derivative of y with respect to t. Well, if I do that, I get, looks like if I set this guy equal to u, du is 2t. So it's going to be maybe 1/2 t. If I go ahead and I multiply, oh, I don't want that. Quit that right now. Distribute the 1/4 in. Okay, I know you're going to want to know how this is happening. So let's do this way. Distribute the 1/4 in, and you'll get t squared, y equals t squared over 4 minus 1. Well, when I take the derivative, this is the only thing that matters, so it's going to be 1/2 t. Hopefully you see that. And that's going to be over dx dt. All right? So dx dt, this is t, actually x equals t to the 1/2 power. Okay? So dx dt looks like it's going to be, I don't know, 1/2 t to the negative 1/2. So I have to make this guy work, all right? Or I have to simplify that, make it nicer. The 1/2 will cancel, and the t to the 1/2, let's bring it up top. So I get as my answer t to the 3/2 power. That is the derivative of the parametric equation. Now, we want to know when when x equals 2. All right? So when, and I'll bring it over here, when x equals 2. Well, we have to find t. You have to find t. So I'll use this equation. 2 is equal to the square root of t. T must be 4. T has to be 4. So you go back, go back to the original equation, use the 2. I could have used the 3 and the y to get the t, doesn't matter. But that equation is much more complicated here. at the hiccups here. Sorry. So I put 4 into this equation, so I get 4 to the 3/2 power, and voila, 8 is the slope at 2, 3. This was the slope formula. I plug in the 4 for the t, and I get 8. And you know, in a multiple choice situation, there's going to be one where it's 2 to the 3/2 power. So, I mean, you can see the difficulty with this. Or I should say the erroneous stuff that can happen. Now, we want the second derivative. So here we go. Let's do the second derivative. So, the second derivative, okay, is equal to the derivative with respect to t of the derivative. All right, there it is. This is the derivative. All right, over. Now, this is the cool part. It's over 1/2 t to the negative 1/2. And if you notice, that was the derivative with respect to x, and that's what this is. All right? So, you know, that is the tricky part of this. And that's why they have this go on. So let's see if we can do this. I think we can. I think we got this. This is 3/2 t to the 1/2 power. And then this is keeping it at 1/2 t to the negative 1/2 power. Let the negative 1/2 power come up. Divide this, you get equal to 3t. That's fantastic. We know what t is from the green stuff here. T is 4, so I get the second derivative at that point to be 3 times 4, which is 12. 12 is definitely greater than 0. Therefore, this guy is concave, if I could spell it rightly. All right, this is concave up. And that's what it wanted to know. My original problem, if I go back here, find slope and concavity. Well, the slope is 8, and it's concave up. Nice. You guys got any questions? If you notice, I'm not in the Library of Congress today. I'm hanging out in my room. All right, a lot of the videos will be shot here because softball's starting soon. It's actually a day before. All right, nice. Let's continue. Let's try another one. Arc length. All right, arc length looks like that. It's the derivative squared plus the derivative with x respect to t squared, the derivative with y respect to t squared. Add them up under square root from a to b. So I think we got one here. I made an example here. I said find the arc length of the curve. So let's take the derivative with respect to x, if you will. I'll call it x prime. And that, I made it nice here. You know what I'm saying? So that looks like t to the 1/2 power. Okay? And then y prime is going to be, we take the derivative, is just looks like 2. That's fantastic. Now let's put it into our equation. It wants it from 0 to 5. So we're going 0 to 5. Square root of t to the 1/2 squared plus 2 squared. So that tells me dt, I guess. Okay. So that tells me this is going to be the square root of t plus 4 dt. Well, I say dt, I write dx. Something's wrong with me. Now, I hope you know how to do that integral. If you don't, I will remind you a little bit. I'm going to set, this is u du, u to the 1/2 power. Okay, if I set u equal to t plus 4, and I set du is dt, if you will. All right, so now I can do this integral. That integral becomes u to the 3/2 power divided by 3/2 or 2/3. I could put the other stuff back in if you want. So that's evaluated 5 and 0. So we'll put the other stuff back in and make it 2 times t plus 4 to the 3/2 power over 3. And that's evaluated at 5 and 0. So I guess when the smoke clears on this, you put 5, you get 9. You get 81, cube root 81, and blah, 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 blah. When the smoke clears, you get 38 thirds as your answer. And that's units, because we're talking about arc length. All right. So, nice. We got arc length. We got taking derivatives of these parametric equations, both first and second derivative for concavity. Let's give you some practice. Why not? Let's go 727. That sounds like an airplane. 727. Let's go 1 to 9 odd. So that's 1, 3, 5, 7, 9. 4 questions. All right. You can practice both of those. All right. And then when we come in class, we'll talk a little bit more. All right. See ya.